All right, we have Don Patterson, and this is his recording coming up.
Hi, I'm Don Patterson.
And I'm Bill Tomlinson, and this is our paper, Proof by Location as a Socially Responsible Financial Infrastructure. So we'd like to start off by talking about what are some of the problems with existing cryptocurrencies. So first off, cryptocurrencies often use large amounts of energy. So for example, Bitcoin uses 707 kilowatt hours per transaction, a number that has been critiqued in both academic and news sources. Ethereum uses 64.2 kilowatt hours per transaction as well. So the use of large amounts of energy is a real problem for cryptocurrencies and potentially limits their ability to become a dominant financial infrastructure because of the social challenges that come along with that energy usage and the CO2 that they produce. A second issue that is perhaps less noteworthy at present, but nevertheless is similarly significant from a social perspective, is that cryptocurrencies tend to contribute to wealth inequality. So there's an index called the Gini index that describes how unequal the incomes and wealth of a certain population is. And with the mean of all countries around the world, the mean Gini index is around 37.6, which is partway between 0, meaning perfect wealth equality, and 100, meaning that one individual has all of the wealth. Bitcoin, however, has a Gini index of 88. So the Bitcoin ecosystem has an Gini index of 88, and Ethereum has a Gini index between 76 and 91, depending on how you count. So significantly more wealth inequality than in other human contexts. So the use of the large amounts of energy is problematic because climate change leads to all sorts of challenges. For example, it leads to sea level rise, which is projected to cause 216 million climate migrants by the year 2050, according to the World Bank. And wealth inequality is also a significant social problem. It leads to increased food insecurity and lowered population health and increased ecological degradation. So these are all some really significant issues that cryptocurrencies in their current form contribute to.
So Bitcoin uses a lot of energy, and all of the digital financial transactions exacerbate inequality, financial inequality. So what have other people tried to try and alleviate some of these challenges? Well, Bitcoin uses proof of work, which is the problematic mechanism by which we achieve consensus in the transactions. Proof of work relies on a number of different computers competing in order to solve cryptographic puzzles. The fact that you've solved a cryptographic puzzle means that you've done a lot of work, a lot of computational work, resulting in a lot of wasted CPUs, a lot of wasted CPU cycles. An alternative to that is called proof of stake. Proof of stake is perhaps most well known as the mechanism that Ethereum 2 uses in order to achieve consensus. Proof of stake, sort of simplified a little bit, allows certain individuals that own a lot of cryptocurrency to consolidate, form a block, and then to sort of assert based on their cryptocurrency holdings that this is a valid financial transaction block. The risk is that if they lie or they attempt to do some sort of malfeasance associated with their assertion that this is a good block, through the mechanisms of the proof of stake algorithm, they risk losing their cryptocurrency. So the argument for why this is a good mechanism is because people who have a lot of currency are incentivized to make sure that the system is sound and continues to work. Another mechanism is proof of authority. Proof of authority is a fairly simple mechanism. It says that there are certain identities, certain people that are trusted in order to form blocks, in order to authorize transactions, and that these identities are known. And so when a block is closed, when transactions are authorized, it is a particular person who has authority in the blockchain to close the block. That's another mechanism. A fourth one is called proof of weight. Proof of weight is a consensus building algorithm that's very similar to proof of stake, although how much you use your holdings as in the cryptocurrency as a kind of weighted vote towards closing a block or a set of transactions. Delegated proof of stake is like proof of stake. It just is offered down to a smaller committee of cryptocurrency providers. And then finally, proof of burn is a mechanism of sealing a set of transactions in a block by throwing away currency and demonstrating that you have thrown away some currency, another attempted mechanism to achieve consensus. So there have been some other attempts at trying to find alternatives to the original Bitcoin proof of work algorithm. We looked for something that was similarly inviolable in the same way that you can't cheat a cryptographic algorithm. Proof of work requires you to do work in order to be able to solve a cryptographic protocol. Proof of stake argues that you must have a certain amount of cryptocurrency, and also through cryptographic protocols that can be validated by looking at the blockchain. Other mechanisms are possible, but we wanted a kind of inviolable principle that we could base a blockchain consensus mechanism on. And we arrived at the idea of using the speed of light. Because the speed of light cannot be broken, we can't go faster than the speed of light, we used that as a mechanism by which we validated that different participants in the blockchain validation process were located a sufficient distance away from one another. We did this by measuring the amount of time that it takes for packets to travel between nodes in our consensus building algorithm. And through the time that it takes for that to happen, we both assert that the block is valid, and we make sure that it takes that double spend attacks are not possible. We, for our method, what we did is we went through and we created a basic implementation of this algorithm in Java, and we ran a bunch of simulations of the protocol running with a lot of agents executing the algorithm, around the globe with simulated times between them, because obviously we don't have a lot of people using this algorithm yet. So that was our approach, and that was what we added. So what I'd like to do now is walk through the steps of our protocol, demonstrating at a high level how it works, and then in future slides we'll step through some of the details. So on this slide here, we have a proposed transaction, a transaction that begins with Anna and walks through 7 different steps of our protocol. Anna wishes to send our currency, Xylem, to another participant, Bob. So she initiates a transaction and sends it to a transaction maker, one of the computing nodes that exists in our network. The transaction maker accepts the transaction on behalf of Anna, validates that she has the currency that she claims to have, and validates any other properties that the transaction maker would like to validate, possibly requiring identity checks, possibly requiring other kinds of properties of the transaction. The transaction maker then holds the transaction until the recipient, Bob, agrees to accept the transaction. This recipient approval process is one of the ways our protocol differs from other protocols. For example, Bitcoin, in which you can send currency to any recipient regardless of their participation in the transaction. Once the transaction maker has received acceptance from Bob that the transaction is desired, the transaction maker passes the transaction on step 3 to the block checker. The block checker holds a transaction pool of transactions that have not yet been placed into a block and therefore have not been officially spent yet. As part of being in the transaction pool, the block checker in step 4 passes the transactions around to other peer block checkers in a gossip protocol so that all of those block checkers have transactions available to them for block making. In step 5, a block checker forms a block and sends the block to a third kind of node in our network called a notary. It's at step 5 where the proof by speed of light occurs. Passing the block around between the notaries and the block checker entails a certain amount of time dictated by the distances between the nodes. That distance is both a proof that the notaries are where they are, and it is a mechanism that prevents double spending because of the necessary delay in passing this packet around, around the globe. So after step 5 occurs, and a block checker has formed a block full of transactions from the transaction pool and had it validated by the notaries, in step 6, the block checker gossips the signed and proven block out to the blockchain, adding it onto the blockchain similar to other blockchain mechanisms. That block is picked up in step 7 by other keepers being a superset of transaction makers and block checkers, who are maintaining the validated blocks between them and keeping track of the blockchain in a way that's typical for other cryptocurrencies. This slide demonstrates the specific process by which a transaction is submitted into the approval pool. It consists of a series of signatures and hashes of a particular transaction so that everyone knows that Anna has initiated the transaction and Bob has approved the transaction. It begins by Anna submitting an encrypted transaction to the transaction maker. The encrypted transaction has a number of inputs that are known, basically solving the UTXO of a previous transaction, similar to the way that Bitcoin operates, and these inputs are known and are visible, so that the transaction maker can validate that they are in fact unspent transactions according to the current blockchain. The outputs, however, are encrypted, and they are encrypted against the public key of the recipient. For example, Bob 1, Bob 2, and Bob 3 in this diagram. Bob 1, Bob 2, and Bob 3 must be contacted through a URL, email, some kind of instant messaging, whatever the transaction maker supports, at which point Bob must respond by decrypting the transaction output and returning it back to the transaction maker. In addition to these encrypted outputs, there's also a transaction maker fee, a fee that goes to the transaction maker for doing this work, as well as a location proof fee that goes to future participants in the proof network. Once Bob 1, 2, and 3 has decrypted the outputs of the transaction, it's now possible to see that the outputs have been signed by Anna and therefore valid because the encryption encrypted the signed output. And so now the transaction maker has access to a transaction that includes inputs that have been validated and a number of outputs that have been decrypted and are able to be passed on to the transaction pool, which can now hold a complete and validated transaction approved by Anna and approved by Bob for inclusion into the blockchain mechanism, included into the block proof mechanism.
To notarize a block, each block checker takes the hashes from the previous blocks in the blockchain and converts them into a set of latitude and longitude locations at various target points around the Earth. The block checker who is closest to the first of these targets becomes the lead block checker and organizes the block notarization process. The lead block checker works with a subcommittee of other block checkers' notaries, each of whom are the closest to one of the other geographic targets, to notarize the block. The subcommittee block checkers perform speed of light location verification on each other and on the notaries that they're working with. They then exchange information about each other's response times. They then compare these response times with the reported locations for each of the block checkers and notaries that were stored on the blockchain previously, and use that information to calculate eigentrust values for each of the members of the subcommittee. The lead block checker then begins a notarization chain, including all trusted block checkers and notaries, that is, those with a high enough eigentrust score to demonstrate that they weren't lying about their position. This notarization chain goes from the lead block checker to each of the other block checkers in turn, who then sends it out to the subcommittee notaries who are nearest to them. Each block checker and notary signs the block before passing it along. Due to the distance between the various subcommittee members, the limitation of the speed of light in this process creates a delay that is analogous to the one created by the proof of work process underlying Bitcoin.
At various points in our block proof mechanism, it's necessary to randomly choose locations on the surface of the planet. So to do that, we use a geographic hash function. Our geographic hash function uses properties of the blockchain to produce random locations on the planet that are not knowable before the previous blocks have been solved. And so it's impossible to pre-compute these locations.
We've performed some initial evaluations on this system, and we have found some promising preliminary results. So first off, it's able to maintain a throughput that is on par with or above all of the other major systems we compared it to, including Bitcoin and Ethereum, both versions, as well as Visa, with the possibility of 125,000 transactions per second. Second, we found that it had a significantly lower energy usage per transaction, several orders of magnitude lower than Bitcoin and Ethereum W, significantly lower than Ethereum, and lower even than Visa per transaction. And you can see the charts here on the slide. In addition, we found that this proof by location system potentially reduces wealth inequality as well. So we created in a simple simulation that compared the system that we're building to Bitcoin, Ethereum, Ethereum W, and Visa, and found that the system that we're creating reduces wealth inequality, that it causes the Gini index to fall, whereas all of the other systems cause the Gini index to increase, which is on par with what we would expect given the information that has previously been studied about the wealth inequality. And this paper has presented a novel mechanism for enabling a distributed global consensus to confirm the integrity of digital financial transactions. The associated platform, Xylem, is designed to have lower environmental impacts than existing financial infrastructures such as Bitcoin, Ethereum, Ethereum 2, and Visa. Notably, it is also designed to distribute transaction fees geographically to support broader participation. The tendency for existing proof-of-stake algorithms to support wealth centralization is a critical and underappreciated shortcoming of previous approaches that our system corrects.
Financial systems are an important part of the global socio-technical infrastructure, and any changes to them should be justified from both a social and a technical perspective. We therefore propose the Xylem architecture that we've described previously, platform and a cryptocurrency, as a step toward providing a better user experience, a better economic infrastructure, and a better social mechanism by which people engage in payments around the world.
We would like to thank the students we worked with on this project, Ethan Banez, Evelyn Chin, Hayden Friedman, Nicole Sullivan, and Ishan Varney for their contributions to the project. And also to Adrian Berthlow and the reviewers of this paper for their feedback on our work. Thank you very much.
Excellent.
Thank you.
Well done. So are there any questions from the floor? Folks, raise your hand, put in the chat, unmute yourself. So I'll get the ball rolling. So in terms of, you were saying you're building this, or where are you in terms of completing it and testing this out on a real life environment?
Yeah, we have a Java implementation that doesn't actually geolocate around the planet. We have simulated locations within the implementation. We've tried to work with the follow-on to Planet Lab, which was this distributed academic set of computers that made themselves available to do kind of test network protocols. But we weren't able to get that to work quite right. So we just had to be satisfied with doing simulated locations. So yeah, we have like an MVP of an agent-based process that builds on all the basic mechanisms internally that could be distributed out if we could get those locations available to us.
And are you also looking into commercializing this, or you plan to hand that over, transfer the license? So what are your thoughts?
Well, we don't really have a commercialization plan per se, apart from possibly working with someone to help us bootstrap the engineering of it, right? So if we were to commercialize it, mostly it would just be commercialized through winning some of those early fees, rather than necessarily having a place to, there's not really a commercial mechanism in it apart from the fee structure. But if you're the first ones in, you get a lot of the fees early on.
All right, great. Any other questions from anybody else on the floor? Yes, I see a question. You want to address that?
Would it work if nodes were all located in a single country? Yeah, it would, because we find the closest location to the geographic hash random locations. So if the closest locations were all kind of far away, it would still work. It would just bias them towards people close to the locations.
Right. Thanks for the question, John. Anybody else? If not, I'll want to go ahead and thank John for the excellent paper and the presentation.
Thank you very much.
Thank you. All right, let's move to the next. Zara Batul, welcome. You're the last speaker of paper number 15708468111, BlockFest, a blockchain-based federated anomaly detection and detection framework with computation offloading using transformers. Zara, go ahead and introduce yourself, then I can play your presentation.
Okay, thank you. Hello, everyone. My name is Zara, and I'm a PhD student at ETS Montreal, and I'm also working with Ericsson. So our work is related to overcome the issue of resource-constrained clients in federated learning. So we used split learning by providing training assistance to clients in federated learning for computational overhead, and we integrated blockchain for securing federated learning ecosystem.
Great, excellent. And let me go ahead and get your presentation going. Thank you. Let's share the screen. And folks, tell me if you can hear.
Okay.
Hello, everyone.
Audio was okay? Yes. Yes. Okay, great. Let's roll.
Hello, everyone. Today, I'm pleased to present our paper that is BlockFest, a blockchain-based federated anomaly detection framework with computation offloading using transformers. So let's introduce my team and myself. My name is Zara, and I'm a PhD student at ETS, and I'm also working with Ericsson as an internee. And I'm working with my supervisor, Professor Kevin, and another professor from ETS, Professor Ulrich, and 2 data scientists from Ericsson. So first, let's go through the agenda of my talk quickly. My talk will have these content. I will begin with a short introduction of my work, then I will jump into research objective. After that, I will discuss my problem statement in light of existing studies, and I will explain every concept that I'm going to use in my work in the background section. And then I will present my proposed solution architecture, that perhaps the main part. Finally, I will present the results and conclusion. As our proposed framework is generic and applicable on various use cases, but in our proposed work, we focus on anomaly detection in communication service providers' data using their key performance indicators. So first we will discuss what is anomaly detection. So anomaly detection represents a deviation from the normal traffic flow, and the unusual behavior may occur because of a sudden spike in traffic volume or system malfunctioning. An anomalous pattern in the temporal data is learned through collecting samples of certain volumes or over a period. And it's important to timely respond to an anomalous behavior for the sake of network reliability, because if a network stops functioning, this may alienate potential users and reduce the reliability of the network. So there is a need to provide more efficient, effective tool to identify the malicious network traffic. So the 5th generation communication networks revolutionized different sectors by providing high speed. So the key performance indicators such as latency, throughput, and cell downtime are closely monitored by operational engineers to check 5G network performance. So to train a more robust anomaly detection model, we need data to be aggregated on the central server. So the main challenge is to access the sensitive data for deep learning model training, as there are different laws that restrict the sharing of users' personal data, and different data communication service providers like ATT and Verizon are often reluctant to share their user data. So this makes the 5G obsolete by restricting its ability to deliver the promised goals. So our main contribution are we developed an efficient federated learning based deep learning framework to detect anomalies in traffic data from a network of communication service providers. We named our solution BlockFest. The BlockFest employs a combination of federated and split learning to train a more accurate and faster deep learning model by securing private data and encouraging resource-limited clients to participate. And a transformer neural network is employed to detect anomalies in communication service provider sequence data. And an Ethereum blockchain-based smart contract is implemented to replace the federated learning server, which orchestrates the federated learning training process while maintaining transparency and traceability. And we evaluated our solution against different baseline, that is centralized, split learning, and federated learning solutions. So let's jump into related work and background section. So by reviewing all previous work, we finally concluded that centralized machine learning model is not efficient due to lack of quality data for training, and clients are often reluctant to share their data, and even data transmission cost is high for centralized machine learning model training. And then the federated learning is proposed to break data silos by providing privacy and quality data for the collaborative model training, but still there are some drawbacks in traditional federated learning system, as it prone to attacks, it is prone to risk of privacy invasion, and in traditional federated learning, resource constrained client may not able to participate due to limited battery life or internet connectivity. The existing blockchain-based federated learning system suffers from limited performance in terms of throughput and processing time. So in the background, I will explain every concept that we used in our work. So as a solution of data transmission and privacy problem, the concept of federated learning was proposed. It allows users to collaboratively train a shared machine learning model without sharing their personal data with a centralized server. So there are two main entities in the federated learning systems: the data owner and the communication service providers, the clients. So federated learning enables client to learn from others without learning about them. It enables communication service providers to perform learning tasks locally and share their locally trained model with the server instead of the data. In traditional federated learning, first server will request for connection, then available clients will respond, and then server select available clients randomly. Server will send initial global model parameter to selected client, and each client use its data to train a local model, and each client will share its local model with the server instead of the data. So finally, all collected local models are aggregated to generate a one global model by the server. So the server send back the aggregated results to a participant to continue the collaborative learning process. As we already discussed in related work limitation, that there is another problem for model training. FL client should have high computation resources to train the model, otherwise the resource constrained clients may not be able to participate. The learning which we are using in our work for sharing the training overhead of clients, the concept derived from the split neural network, in which half of the network is trained by one entity and other half is trained by another entity. So split learning, each client compute a partial deep network up to a specific layer, and the output, and referred to as the cut layer, the output of the cut layer sent to the server for further training, and then server will forward propagate and then again back propagate, and will send the activation to the clients, and the client will receive the gradient at the cut layer and will do their side of the training. So the benefits of integrating blockchain with federated learning is that we don't need a trusted third party, as we have smart contract. It will ensure transparency to help federated learning build trust. It will replace federated learning server by orchestrating federated learning through automatic round selection, federated learning round selection, and aggregation phases for multiple federated learning tasks. It will record every action of clients on the blockchain, immutable ledger, as we don't trust client. It helps in audit trail, and as we can't trust the aggregator if it's involved in intentionally spamming local model of the clients. So we use the anomaly transformer architecture proposed by Zhu et al. It used the anomaly attention block and feed forward layers. It has an anomaly attention block with a two branch structure, that is prior association and series association, and the min-max strategy is used to make harder the reconstruction of anomalies, so that can be spotted more easily. And in the minimum stage we minimize the discrepancy, and in the maximum stage we maximize it. Then we calculate the reconstruction loss and the overall association discrepancy, and that give us the total loss. So this is a proposed architecture. We proposed hybrid protocol which utilizes the strength of split learning and federated learning to enable parallel processing of model training among clients. So we have federated learning server, split learning server, blockchain, and off-chain storage. And I will explain the functionality of the system in the next slide in the system sequence diagram. So this is the sequence diagram which is illustrating how the system is working. So first, the blockchain-based server initiate the process by sending initial parameter of the global model to the clients, and then the clients will start training their local model by performing forward propagation until the cut layer, and the client have the input MLP, the minority of the transformer layer, and the output MLP. And they compute the output of the cut transformer layer and send them to the server. The server computes the majority of the transformer layer and send back the output of the transformer modules to the clients. After receiving the local model updates, the client will start rest of the training. Client receive it and will pass it through the output MLP to get the reconstructed input. We used U-shaped split learning architecture there, where the labels are not shared with the server, and server has no access to it. So then clients will calculate the reconstruction loss. So beside reconstruction loss, anomaly model is optimized by the min-max strategy to constrain the prior and serious association for more distinguishable association discrepancy. So the client will push their local updates to often storage, that is IPFS, and then each client has their model stored on an often storage and hash of the model on chain. So when client will finish training, the global aggregation will be performed by the federated learning server. So it will retrieve all local model from IPFS by comparing with their on-chain hashes to perform aggregation for global model. So this will complete the first round of training. So now we will present the results. So there are tools which we use for the development of the system. So Solidity is used for smart contract, Truffle is used as a development environment, Ganache is used as test Ethereum network, Web3 provide communication interface with contract, Node.js required because of its dependencies to run Truffle, and then PyTorch or deep learning framework is used. IPFS is used as an off-chain data storage. So we have a total of this number of samples of communication service providers data distributed among 5 cells. So data had 820 different features representing CSP cells performance. For methodology, we start with filtering important feature. We selected KPIs, so the remaining features were 12. Then we remove features having null values less than 80%, and the other missing values are imputed with mean value. And this is followed by the creation of the data sequence for preparing data to apply transformer neural network as our CSP's data recorded at 1 hour regular time intervals. So these type of data are often noisy and incomplete due to faulty devices or communication error. So we create sequence by removing recorded data of less than 24 hours. Then we perform the exploratory data analysis to investigate data further. After that, we employed isolation forest algorithm for labeling our unsupervised data. Then we built a centralized model by using the transformer neural network. Finally, we built our blockchain-based federated split model. So here is the performance result of our proposed solution. We use term centralized solution is for simple transformer model. The decentralized solutions are transformer model with federated learning, split learning, and BlockFest, which is a combination of both federated and split learning with blockchain. We use the performance metrics like accuracy, precision, recall, FN score, area under ROC to evaluate our system. We executed our experiment for 20th FL round. It can be seen that the centralized solution achieves accuracy up to 90% for 20th round. And if we compare results to our proposed setting, which is BlockFest, it achieves accuracy up to 86%, and recall and F1 score is good for BlockFest than centralized. So we evaluated the time and gas cost of our proposed solution, that is BlockFest, with other baselines. The bar chart is showing the execution time for centralized for different settings. And the centralized model is taking less time to execute, while FL is taking a bit more time to execute, as it involves aggregation, communication with clients, and training of rounds. And the split learning is sharing overhead of training with clients, so it takes more time as clients need to send activation and to receive activations for back propagation, so it takes more time. And the combination of federated split learning exhibit greater increase in time over traditional split learning. And finally, our proposed blockchain-based solution is delayed up to 15%. And for line plot at right side, we evaluated the gas usage against every round of federated learning. So in graph, the gas usage for first round is high as compared to other, because it also involved the cost of smart contract deployment. To sum up, we proposed BlockFest, a deep learning framework which combines the best of both federated learning and split learning by allowing clients to train a collaborative model with computational offloading. Our case studies show how resource-constrained clients can participate to detect anomalies in real-time IoT system, and our solution achieves an accuracy of 86%, which is competitive with others, while providing additional benefits in terms of decentralization and client-side offloading. And our solution will allow Ericsson like it's ensuring a more robust anomaly detection model for critical key performance indicator, and it will allow Ericsson to respond more proactively to cell outage. And the use of blockchain will generate an audit trail that can be used to address any challenges from the customers to take corrective actions. Thank you for the attention, and I'm looking forward for the questions.
Right. Great. Thank you, Zara, for that excellent presentation. To get going, question one, how long you all have been working on this particular system, developing this?
Sorry.
How long you have been working on developing this?
So, okay, I'm working from the last year.
Mhm. Okay,
I was also writing patent about this, but the idea was published. Now I'm working on the papers.
and where are you in the journey of completing this? The team, that is.
Sorry, I didn't get you.
So where are you in your journey for completing the work?
Yeah, of course, we need to extend this on journal side too,
Right.
because we need to work on the privacy part, as the clients need to train half of the model with on the split learning server for sharing the computational overhead. So next we are working on the privacy part to overcome this issue.
And also on the privacy, are you looking into the security aspect as well?
Yeah, of course, the security of the, like, from even in federated learning from client local model, the malicious server can regenerate the input from the local model. So maybe we will use some differential privacy techniques to overcome this.
All right, anything else, folks? Any other questions for Zara? All right, so I'll go ahead and stop the recording. With that, first of all, I would like to thank all the authors and the speakers who have presented today.
Thank you.
It's very clear that all of you have been working on extensively, diligently on your project. These are pretty exciting, complex projects. Happy to have you all part of the GET Forum. And I'm going to stop the recording, but open the floor for any discussion and general feedback.